So I'm going to tell you first of all about a typo in the book that I added to the errata, but I forgot to upload the erratum file to the class website. So let me show you the typo. It's here. The cross section for scattering off a hard sphere turns out to be 4 pi r0 squared. That's twice the classical value, not 4 times. I somehow saw the 4 here and typed in 4 times. I think what I'm going to do first is go through an example about Legendre polynomials. An example that complements one of the homework problems. I realized that homework problem was, I think, already due, but in any event, well, the object here is education rather than getting the grading done one way or another. So let's consider the potential outside a charged circle. And let me get some of these paper stuff out of the way. And I can, and let me also move this thing out of the way. And let me also start a chat thing so that if people want to chat, they can type there. So let's suppose we have a ring. Now I made a ring and bingo, it changed. I mean, I don't know what the hell is going on with this thing. So I'm going to go. All right, now I've lost everything. So let me just say 9 November. Good Christ. I think it's my sleeve here. Or it's the new software. I don't know what the hell it is. So let me try again here. 9. This is just so annoying. Now I'm going to move this out of the way and see if I can do. So 9 November. And frankly, I've gotten so distracted by this stupid software. So we're imagining we've got a circle of radius A, and it has charge Q. And if I switch now to blue, we can have an x-axis going this way, a y-axis going this way, and a z-axis this way. And if we're at distance r, so let me maybe switch to black now. So we're at a point here that's a distance r up the z-axis. And what's the potential at that point? Well, that is given by this equation 9.91. In other words, it's the potential here, phi of r, but 0, and the theta is 0. Well, this is just the charge Q divided by 4 pi epsilon 0. And then the distance. Well, the distance is the square root of r squared plus a squared. So we divide by the square root of r squared plus a squared. So this is the way one starts the homework problem. But what I'm going to do is not the homework problem, but the alternative problem. The alternative problem is to find the potential outside the circle, or to put it differently, outside of a sphere of radius a centered at the origin. Well, what we do is we go back to the general formula for an azimuthally symmetric system, and this is azimuthally symmetric because it's a circle in the XY plane, so there's no phi dependence. And the general expression then is here. Now, if you're doing in the homework problem, you had to throw out all the BLs because they would diverge at r equals 0, and you were asked to find the potential for r less than a. Whereas here I'm asking you to, here I'm going to work out the potential for r greater than a. Well, it's the same formula, but the coefficients will just be different. And in particular, the only r to the L term that can survive is for L equals 0. The others diverge at infinity. And obviously the potential isn't going to be infinite due to a ring of charge Q. The potential will go to 0 as r goes to infinity. And since the potential goes to 0 as r goes to infinity, even a0 has to be 0, because that would give a constant potential at infinity. And so what we do is we write it in this form, and then we set a0 equal to 0. But now what we do is we re-express this formula, pulling out the recognizing that r is greater than a. So we pull out an r, and we have 1 plus a over r squared, where a over r is going to be small, or at least less than 1. Now, back in the chapter on infinite series, chapter 5, we showed how to expand such an inverse square root, and copying that formula, we can write the potential on the z-axis at a point r above the xy plane as this power series in a over r. And what I also did here was I had an r here. This power series is a power series in 1 over r to the 2n, but I took this r and made it r to the 2n, and then I canceled the extra a by putting an a there. And this is what we have. And so then what we know is that this general solution, well, we're going to set a0 equal to 0. And now what we do is we just set, we have, let's see, maybe I'll switch to a different color. We'll set my, why did it switch on me to, what the hell is going on with this? I really am beginning to dislike Apple. In fact, I could tell you some horror stories about the Apple store on Louisiana, but I won't use up class time with that. So I've forgotten what I was saying because it's so distracting when the screen goes nuts. So we know what all the coefficients are, and we get this expression. And so this is the general formula. In other words, we know phi of r0 looks like this, and we know it's of this form. And yeah, what I was going to say was minus L minus 1, which is this power, we're going to set equal to minus 2n minus 1, which is the power of r here. And that then says that L is equal to 2n. And so in this sum, we just have P2n. And so we we say, in other words, the thing that multiplies this, the Legendre polynomial, is P2n that multiplies that. So that's our Legendre polynomial. The fact that it's even powers here is, I think, that you expect the potential above the xy plane and below the xy plane to be the same. And so when theta is greater than pi over 2, in other words, the cosine looks like this. Maybe I'll switch to a different color, yellow now. The cosine curve looks like this. So this is 0 and this is 2 pi. And so this is pi over 2. And when theta is pi over 2, what one has is the xy plane. And then as you go below, the cosine goes negative. It goes from positive to negative. And so you want even powers of cosine theta. And that's what you get with P2n. You get these even powers. Let's just see if we can see why it is. Well, yeah, all right, we can see it just by examples here. P2 is x squared, is x to the 2 and x to the 0. P3 is x cubed and x to the first power. P4 is x to the 4th, x squared and 3. So it's basically powers of it's even powers. Pn for n even has even powers of x, and Pn for n odd has odd powers of x. So that's why this works out in this way. So this is the solution. So let's see, that's two things that I wanted to do today. The other thing I think probably which would be most useful would be, first of all, to go to Bessel functions. And we were talking about spherical Bessel functions last time. And remember this Rayleigh's nice formula and this nice recursion relation. This is the orthogonality relation. This is the completeness relation. Just let me switch maybe to black for a moment. This completeness relation, just to clarify it just a little bit, it can be 2r squared over a cubed. And then a sum n equals 1 to infinity of then here this JL of ZL n R over A, JL of ZL n R prime over A, and then divided by J squared L plus 1 of ZL n. So that's the delta function relation. And then there's a continuum relation. The one I just wrote down allows you to develop these formulas. And I could, by the way, have had R prime squared here. Or one could one could apportion the power of R to partly to R and partly to R prime. I think I'm going to skip all that. We did that last time. One of the things that's important is this plane wave expansion. This is what's often used in scattering theory, non-relativistic scattering theory, or even, I guess, relativistic. E to the I k dot r is then this sum, 4 pi I to the L JL of kr. And then the spherical harmonics, one of them, the theta phi for the vector r, and theta prime phi prime for the vector k. And that then is used in this expression. It shows up again in this expression where we're dividing by 2 pi to the 3 halves, because that's the usual way of normalizing the phase factor. Something that confused me in the lecture last time. The point here is that you want to deal with tiny kr. So it's kr that's tiny, and so that's why the probability is small. It's kr to the 2l plus 3, and so so in other words, it's not simply that for high L, the probability is small. It's that for high L, the probability is very small, provided kr is small, because it's a power of KL. And for L equals 0, it's just KL cubed. And and part of that, in fact, is just taken up by the volume of the sphere, which is 4 pi r cubed over 3. So it was tiny kr here. That's the point. And so I added, I had previously tiny r. It's tiny kr. K, of course, is the momentum apart from a factor of h bar. And then there was this expression for what happens to the JL of KR for, this is for large KR now, is it behaves as a trigonometric function, in fact, sine KR minus L pi over 2 KR. And that is exactly this. And so the actual scattered ray wave is going to have a wave function that is going to be very close to that. And the distinction is that there's an extra phase, a phase shift that occurs here. And when you work out what the cross-section is, it turns out that the total cross-section is a sum of these phase shifts. And for each L, what you have is the partial wave cross-section. Okay, so quantum dots, we went through this to some extent last time, and the model here is a single electron that's trapped in a potential that's spherically symmetric and infinite outside for r greater than a. And that's why these ZL, these zeros, so for r equal to a, it's JL evaluated at the nth zero of the Elf Bessel function, so that's 0. The reason it's actually 0 is that the potential is infinite. If it were a finite potential, then there'd be some leakage of the function into the region r greater than a. The Bessel functions of the second kind are these Neumann functions, and they're singular at the origin. Let me see. For a coaxial cable, well, there you use the Neumann functions that are of just the ordinary Neumann functions of the cylindrical Bessel function. And I think I went through that last time. Let me just make sure, because I wouldn't want to. It's possible that I added an example. Oh, I don't think so. This is, yeah, all right. So I did add a little bit. Did I show you all this last time? Can somebody type something in the chat? Did I go through the details here, or is this new? I think I might have. Well, at the risk of boring people, I'll go through it in a little more detail, because I think this is stuff that I added after class on Tuesday. So an ideal coaxial cable is, did I say, perfectly conducting for rho less than R0 and for rho greater than R, vacuum in between. Rho equal to 0 is not in the physical domain, so we have to use the Neumann Bessel functions as well as the ordinary Bessel functions. And then in the region that's vacuum or plastic or wax or air or something, they approximately obey the vacuum Maxwell's equations, these two equations, and they relate the rho and phi components of E and B to the Z components of E and B. We then have the electric and magnetic field satisfying the boundary conditions that the tangential electric field vanishes on the conductor, and the normal magnetic field vanishes on the surface of the conductor. And so then one can show that you satisfy the boundary conditions if you have this combination vanishing. And that's actually, I probably should have written this as JNYN is equal to JNYN with the V hopping from the Y to the J. V is the ratio of the radii, and X is this square root here. So going back then to spherical Bessel functions, scattering off a hard sphere, one has to use both Bessel functions, the ordinary and the Neumann Bessel functions. And then since it's a hard sphere, when R is equal to the radius of the sphere, the function U has to vanish. And so that sets what the ratio of these two coefficients are, CL and DL, because this linear combination has to vanish when R is equal to R0. Anyway, one then finds that that for L equals 0, the ratio is the tangent of KR0. That's because the zeroth Neumann and spherical Bessel functions are very simple, and you then get that U0 is the sine of KR minus KR0 divided by this constant, and you find the phase shift is KR0, and then the cross section turns out to be 4 pi R0 squared, which is twice the classical value. And you can work out the P wave one like that. What to do next? I think maybe the thing to do next is to maybe start doing some of the, to do one maybe of the problems that won't be due next week, but the week after next, the 21st or so. It's almost Thanksgiving. And so let me jump over here to the general relativity chapter, and in particular, the exercises there. And in fact, let me also get rid of that so it doesn't blot anything out. So I think what I assigned as homework problems, again, not due till the 21st, I think, is the first one and the third one. So maybe I'll try to do for you in real time the second one. And so as to not waste your time, I'm going to actually look up the solution so that we save time here. So the basic idea here is that, let me change colors a little bit, maybe to blue. So the basic idea is that we're saying that dp is x hat, well, dx plus y hat dy plus z hat dz, where the hat is generally means unit vector. And we're thinking about flat space here. And so we want to compute what the change in dp is due to d rho, d phi, and dz. And that will give us formulas for rho hat, phi hat, and z hat. And so the basic vector, or the basis vector E, that was supposed to be an E, but I was thinking rho, so let me undo it. E rho is then the partial of the point with respect to rho. And we can, in fact, maybe I should, instead of copying this on the screen, I'll just sort of show you the solution. So so the basis vector E rho is the partial of P with respect to rho. So when rho changes, you go in the X direction and you go in the Y direction, but so in other words, you're going at distance rho, and if the point is here, then when you change rho by going a little bit this way, you go as cosine of this angle phi. So this angle here is phi, and then you go sine of phi in this direction. So projecting this distance here, which is say d rho, down here we get cosine of phi times rho. And then if we go this way, I haven't really done that correctly, but this distance here, let me switch maybe to green. This distance here is rho, or d rho, sine phi. And so, in fact, this one was d rho cosine phi. And so the change in the point is actually, I'm a little puzzled here. Right. Actually, it's that's curious. You see, the well, I've skipped ahead too much here. The change in x is cosine phi d rho. The change in y is sine phi d rho. And so the change in the point is x hat cosine phi d rho plus y hat sine phi d rho. So the basis vector e rho, which is how the point changes when you change rho, is x hat cosine phi plus y hat sine phi. And then similarly, the basis vector e phi. So oh God, e phi is the partial of the point with respect to phi. And now, if we look at the formula for A, in other words, we say here x is rho cosine phi and y is rho sine phi, then when we change phi, dx is equal to minus rho sine phi d phi, and dy is rho cosine phi d phi. And so then the change, so those are the changes in x and y, and the change in the point then is x hat times dx, which is minus sine phi d phi, plus y hat times the change in y, which is cosine phi d phi. And so e phi is just partial, the derivative of p with respect to phi, and so we just cancel out the d phis and we get that phi hat is, so let's see, I don't know if I want to write all this down since we've seen it on the screen, but it's minus x hat sine phi d phi plus y hat cosine phi d phi. So e phi, which is partial p, partial phi then is, which is phi hat, is equal to minus x hat sine phi plus y hat cosine phi. And then, well, Ez is the partial of p with respect to z, and that's just z hat. You might wonder, what are these little e's? Well, that's something that was, here, let me blow that away and go back here to something like, actually, we didn't do tensor equations before, but these e's, I'm just skipping ahead to say what it, okay, so these basis vectors are just the derivative of the point with respect to a coordinate, and that's how I was using them here. And since the points, oh my goodness, I just now saw the notation on the chat. Sorry, very sorry, that was stupid of me. So there is the screen, and maybe I'll move this out of the way for the moment, and I can even make this a little bit bigger. So this is what I was showing here. I hope you saw all the Bessel stuff. So the idea here is that you have a point and you describe it by coordinates, and when you change the coordinates, then this thing here is a basis vector in the sense of how does the point move as we change the coordinates, and so it's in this case it turns out to be for E phi it turns out to be this combination. For EZ it's just how does a point change when you change Z? Well, it just goes in the Z hat direction. What is nice about these things is that maybe I'll go through a little bit of this, and which I'll be repeating tomorrow. So here I've defined the basis vector as the ith basis vector is the derivative of the physical point with respect to the ith coordinate. And since P is invariant, this is just going to transform like a derivative, and that's what defines a covariant vector. So in the primed coordinate system, E prime of E prime is the partial of P prime of X prime with respect to X prime I, but P prime of X prime is just P of X because this is the physical point, and whether you describe it with the prime coordinates or the unprimed coordinates, it's the same point. That is to say, in the prime system, P prime of X prime is P of X. And so what is this derivative? Well, remember, the way any of these things transform is a ratio, is a partial derivative of components. And what you do is you have a prime here, and you have the ith variable and carries the prime. And since it's lowered, you put it in the denominator. And then the other thing that you have to sum over by the chain rule goes in the numerator. So you have partial xk, partial x prime I, times the partial of P of X with respect to xk. And that gives you then this partial derivative. This thing is the basis vector in the other system, in the, so to speak, standard system. So small changes in the coordinates give you a small change in the physical point, and they would be then the basis vectors times these changes. And what one can think of then is that the dot product of these is, well, let's suppose we just take the dot product of two changes in the physical points. So this is EI dxi dotted into EK dxk. So that is going to be dxi dxk, and then the dot product of the two EIs. And that dot product then is what we call the metric of space-time. So we can have various examples here. You can think of the surface of a sphere in 3 space. So this is E theta then is the derivative of the point on the sphere with respect to theta. And the points on the sphere, of course, are R sine theta cosine. If the sphere has radius R, sine theta cosine theta, sine theta sine phi, and then cosine theta And so the theta derivative gives you this, the phi derivative gives you that. And then if you take the dot products of these, you get the metric on the sphere, and it turns out to be a two-dimensional, a 2x2 matrix of r squared 0, 0, r squared sine squared theta. And the determinant of that, of course, is r to the 4th sine squared theta. E theta dot E phi vanishes, which is why we've got zeros here. The infinitesimal distance then is E theta dot E theta, E phi dot E phi, and that's then r squared d theta squared plus r squared sine squared theta d phi squared. And I'll just say that if you change coordinates, you get it in this form that is the form that people have been using for the standard cosmology and actually in pore space. And it's just changing from an angle theta to a radius given by some radius of the universe times sine theta divided by some scale factor A. And actually, now that I think about it, why do we have a scale factor if R and capital R are both distances? So let me just think about that. I think that A is extraneous. I skipped over something which I should have, I think. Well, let's just mention this about tensor equations. As I said to you last time, one of the basic insights of Einstein was that if you had if you wrote physics in terms of tensors and tensor equations, then the equations would look the same in any system of coordinates. And so, for example, Maxwell's homogeneous equations are tensor equations. And you might say, well, this is the derivative of a tensor of rank 2. Maybe it's not covariant. And in fact, it is, because F is anti-symmetric. Fjk is minus Fkj. And so these are generally invariant tensor equations. And so these are the homogeneous equations. And here the inhomogeneous equation is when you write it in terms of the space-time metric, it's the derivative or the gradient of the square root of g times Fik is square root of g times a current. These are Maxwell's equations in general covariant form, and the equations of Einstein's equations for gravity are, we'll get to R much later, several days, a week or two after Thanksgiving, maybe. Rik minus a half gikr is Newton's constant times 8 pi over c to the 4th times the energy momentum tensor of the matter fields. And so you have a real dichotomy here. You've got gravity on one side, and then on the other side, apart from g, you have, which is a constant, of course, you have the matter equations. I guess the thing that I did skip over, actually, you know what? Why don't I jump back to this chapter on special relativity and just mention something to you that's, this is just notation, but it's used in physics, and it's worth knowing about. So we have, of course, dxi prime is this partial times dx, and these are, as I said to you yesterday, these are the covariant vectors, and the differentials of the coordinates are contravariant vectors, and altogether what you've got is something that's called a one form. And so in other words, you have the coordinate differentials and a covariant vector, and you just sum over k from 0 to 3 if you're in our universe, or sum over whatever in some other geometry. So this idea of a form was introduced by Cartan, who actually was the son of a blacksmith. So he was not one of the aristocrats, but on the other hand, he was the smartest man in France at the time. So he introduced something called the wedge product of two coordinate differentials, and it's basically the directed area spanned by the two differentials. And in this, it's directed in the sense of being either, if you have two differentials, then you can think of the area as pointing this way, or the area is pointing that way. And in recognition of that, dx wedge dy is minus dy wedge dx, and just if this is dx and that's dy, and then the area is this rectangular parallelepiped. Actually, maybe you weren't seeing that. Well, maybe here I'll do it on the board. Here, if you have, this is dx, that's dy, and they aren't necessarily perpendicular. Then you have an area here that's given by basically the cross product of the two, if you're in three space. But more generally, it's just the length dx times the length to the number dx times the number dy, and then it would, well, if they are, you'd need to consider what the angle is. Anyway, the point is that you have the area you consider as perpendicular to dx and to dy, and you can have them go in two different directions. And so that's why you have dx wedge dy equal to minus dy wedge dx. And dx wedge dx, well, that's the area of there is 0 because the two dx's are parallel. But now, what's nice about this is that if you have du wedge dv, well, then you have this structure here for du, and this is dv. And when you wedge it out, what you get, it turns out, is the Jacobian times dx wedge dy. And this is, in fact, what we learned way back in chapter 1, namely that the area, if you change coordinates, the area transforms like the Jacobian, which is the determinant of the matrix of derivatives. So it's partial u, partial x, partial u, partial y in the top row, partial v, partial x, partial v, partial y in the bottom row. And the directed area du wedge dv then is this determinant times the directed area of dx wedge dy. And this dx wedge dk, dxi wedge dk, that's something that is a rank 2 contravariant tensor. And if you multiply it by a rank 2 covariant tensor and then sum over I and k, you get something that's invariant under changes of coordinates. And this is called a 2 form. More generally, a p form is you take p of these dx's and you multiply it by a covariant tensor of rank p, and conventionally you divide by p factorial. Anyway, this is a nice notation. We've kind of run out of time. Tomorrow maybe I'll go over this notation again, as it's just a very it's a very cute notation, and it's just one of these things that Cartan invented, and it was the stuff he did was quite remarkable. All right, I'm going to stop now. I'm sorry about blocking the screen. I think the best thing is when I'm doing something dumb like that, you can try for a few seconds to write on the screen, but if I don't see it, the best thing maybe is to just shout. I guess the main person to shout would be the grader. So if the grader will please shout, give me a second to realize what the chat screen is saying, or to fix it on my own. But otherwise, if I've blocked one of the screens, then the grader should shout out at me, or if the grader doesn't, then somebody else should. All right, so I'm going to stop. Wish you all a nice evening, and see you all tomorrow at 5 o'clock. Bye.